Hey guys, Mr. B here, and in this video we're going to be going through Chapter 8, Section 4 on polarity, polar bonds, and molecules. So, this is not going to be the whole section, it's actually only a part of the section, and that's mainly because there's some other stuff in the section that's a little bit more complex that we really don't need to get into. So, we're primarily just going to be talking about polarity in this section, and what that is. You might have even heard this word before. You might have maybe sunglasses that have polarized lenses. So we're going to talk about what that means, okay? So, bond polarity. A concept we need to understand when we talk about polarity is this concept called electronegativity, okay? And what exactly that is and how does it work? So, a lot of times when atoms are bonded to each other covalently, you might think that they are sharing these electrons between the two atoms equally, right? So like the electrons are sitting in the middle and they're part of this atom and they're part of this atom and they're like shared, between both atoms equally. And in actuality, that's not the case, okay? Now in some atoms that is the case. And when that happens, we basically have a bond where each atom is pulling on the electrons in the middle equally in opposite directions. And we would call this a nonpolar covalent bond. Okay, so the electrons are shared equally and they sit right in the middle of both of these atoms, and they essentially are both atoms' electrons. This is a nonpolar covalent bond. So you might think of this like a game of tug of war where you've got two teams and they're both trying to pull the rope in their respective directions, but they're in a standstill, right? So they're both pulling equally, and therefore the rope isn't going one way or the other. But in a lot of atoms, it doesn't actually work this way, okay? In a lot of atoms, what will actually happen is one of the atoms will tend to pull electrons closer to it and further away from the other one. And so when that happens, you're going to get a charge that's sort of more negative on one end of the atom and a charge that's sort of more positive on the other end of the atom, okay? Now, this isn't going to be fully charged like ionic compounds, where you've got a fully negative part and a fully positive part, and you got an anion and a cation. It's only going to be slightly negative and slightly positive, okay? The electrons are still being shared, they're just not being shared equally. This is what we call a polar covalent bond, or essentially polarity. And this is where we have a bond where you have two atoms and the electrons are not shared equally. So electronegativity is a term that we use to talk about how badly does an atom want electrons. The more electronegative an atom is, the more it tends to want to pull electrons towards it, okay? The less electronegative it is, the more likely it is to want to kind of push electrons away from it. So when you have an atom that is more electronegative than another one, the more electronegative atom will tend to pull electrons closer to it and give it a slight negative charge. And the less electronegative atom will then have a slight positive charge because the electrons have kind of been pulled away. Now, they're not getting fully pulled away, again, like in an ionic compound where you've got this atom took all the electrons and this atom has no electrons anymore. They're still shared, okay? The electrons are still shared in between the atoms, but they're just kind of shifted one way versus the other. Okay, so this is what we call polarity. So we have a chart here, and I'm going to zoom in on this to see it better. And this chart has values, okay? It has electronegativity values. And these values essentially tell you how electronegative the elements are. Maybe this is a little bit too zoomed in. You can switch this out a little bit. There we go. So the most electronegative element on the periodic table is fluorine, okay, in the top right-hand corner. And as you go down and to the left of fluorine or away from fluorine, the electronegativity of atoms decreases. So the least electronegative element is francium in the bottom left. Now, if you take an element like fluorine, which is very, very electronegative, and you bond it up with another element which maybe is not quite as electronegative, like hydrogen, you're going to have a difference in electronegativity values. And depending on how large that difference is, you're going to get a different type of bond, okay, or a different type of covalent bond. So we have a little chart here that can help us to know what the different types of bonds are. But if you have an electronegativity difference between 0 and 0.4, you have a nonpolar covalent bond, which just means the bond is nonpolar. The electrons are going to be sitting right in the middle, in between both atoms, balanced out, completely shared equally. If you have a difference of between 0.4, 0.5, and 1, now you start to get a bit of a polar bond, where one of those atoms is going to have a slight negative charge on it because it tends to pull the electrons towards it, and the other atom will have a slight positive charge because the electrons are getting pulled away. If you have a difference between 1 or 1.1 and 2, now you start getting a very polar covalent bond, where the electrons, again, are still shared between the two atoms, but now they're much more shifted towards one side versus the other, and you have a much more slightly negative charge on one end of the atom or molecule, and one end that is slightly more positive. And then when you get a difference that is 2 or greater, at this point it is ionic, in which case the electrons are not being shared anymore. Okay, this atom has taken all the electrons, this atom has lost all the electrons. Now you have a full negative charged anion and a full positively charged cation, and we are ionic at that point. Okay, so there are lots of molecules that are polar, and oftentimes polar molecules will have some interesting properties. Okay, some very interesting properties. So water is a polar molecule, and so polar molecules in general, because they have a slight negative end and a slight positive end, they tend to have the ability to interact with ionic compounds pretty well. Because remember, ionic compounds have full negative ions and full positive ions. So polar molecules are sort of like ionic compounds in the fact they have slight charges and they can interact. Because water is a polar molecule, it's very good at interacting with ionic compounds in the fact that it can dissolve those ionic compounds. And so what happens when you dissolve something in water is the negative end of the water molecule will attract to the positive part of the ionic compound, and the slightly positive end of the water molecule will attract to the negative end of the ionic compound. And so what water can do is it actually pull these ions apart, and that is the dissolving process that you're seeing, which is why so many things dissolve in water. Now, obviously, not everything dissolves in water, and that's mainly because not everything is an ionic compound. Covalent compounds, which are nonpolar, so they don't have any charges, do not dissolve in water. Prime example of this is oil, right? Oil is nonpolar. It does not have any charges, therefore, water has no effect on oil. So there's other things like plastic, right? Plastic also doesn't have charges. It's nonpolar, doesn't dissolve in water. Okay, so there's lots of things that don't dissolve in water, but water is very good at dissolving a lot of things because it is a polar molecule. So a molecule that has two poles is what we call a dipolar molecule or a dipole. You don't need to worry about that term, but anyway. So other than the fact that polar molecules are good at dissolving a lot of things, the other thing is they will interact with magnetic plates and magnetic fields. So when polar molecules are placed between oppositely charged magnetic plates, they tend to orient themselves in respect to the magnetic plates, right? You got a positive plate and a negative plate. And so, imagine that we have all of these, now these are hydrogen chloride molecules, okay? But imagine that these are water molecules. And you put them inside of a magnetic field and you turn the magnets on. The slightly positive end is going to shift and point towards the negative plate, and the slightly positive end is going to shift and point towards the positive plate, or the negative end is going to point towards the positive plate. And so this is really interesting because it allows us to image things using polar molecules. And so one machine that you probably have heard of before, now whether or not you've actually had this done to you depends on if you've injured yourself badly enough. I know I have. But an MRI machine is known as magnetic resonance imaging. Okay? Basically what an MRI machine does is it creates a giant magnetic field inside this tube. And so you go inside this tube and they turn on this giant magnetic field, and all of the water molecules in your body will orient themselves in a very specific way based on the magnetic field that's being created by the MRI machine. And the cool thing is if you have some kind of abnormality inside your body, like a tumor or maybe some kind of, tissue, something or other they're trying to look for, the water molecules inside that tumor or inside that tissue are not going to be able to orient themselves the normal way that all the other water molecules in your body can do. And so when they take an image of your body with this magnetic field on, everything's going to look normal until they see that part of your body where the water molecules aren't able to orient themselves properly, and they're going to go, ooh, that looks different. That's probably something we're looking for, right? That could be a tumor, or that could be some tissue swelling, or that could be whatever. And that's essentially how an MRI machine works, right? And this is why MRI machines are used for muscle and tissue, where there's a lot of water molecules, and not bone. Okay, bone, there's not really water in your bones. Water is going to be found in your soft tissue. So again, polar molecules kind of have some cool interaction like that. Polarized sunglasses, I mentioned at the beginning of this video, also have basically, molecules in the lenses that can orient themselves different ways. And when they interact with sunlight, which has energy and UV rays and charges on it, the polar molecules in the lenses will essentially change the way that they are oriented, and that can then cut down glare and cut down, highlights and stuff like that to essentially give you a better image when you're looking through these lenses. And that's how polarized lenses work. So super cool, little interesting tidbit there, but either way, that is polarity. So that is it for this section of notes, guys. Hopefully that makes sense. But again, as always, if you have any other questions, make sure that you reach out. Okay, send me an email. You can chat in class, or, if you always ever want to do a one-on-one Google Meet, do some tutoring, I have no problem doing that. So, all right, that's it for this section, and that's it for the chapter. After this, you'll be doing your review and taking your test. So, I'm Mr. B. Thanks for watching. I'll see you in the next one. Bye.